My project is simulation of artifacts in diffusion-weighted MRI. So personally, I hope this project can help me get a big picture of the MR imaging process, because I feel from class, although I know each component of the MR imaging well, I didn't get an overview of how these components relate with each other. So this project can provide a chance to put them in an integrated framework. And second, I hope it can help me better understand the principles of diffusion-weighted MRI, also abbreviated as DWI. And third, it can help to provide ground truth data for validating post-processing methods, which would be related with my current research. The deliverables of this project would be first, the simulation of diffusion-weighted MRI, DWI, and second, the comparisons of DWI appearances in low and high field, and third, I want to learn how the motion can impact image quality. So the motivation for this project is because DWI is susceptible to a number of artifacts. For example, it is highly sensitive to physiological motion. And so this project can provide the objective comparison of different artifact correction methods, because in real life there's no ground truth for artifact correction, but we can do that from simulation. So the method I used is described in this paper. Basically, the framework takes a segmented geometric object with specified MR parameters for each tissue types as input, along with a pulse sequence, and it uses spherical harmonics fitting to simulate the diffusion-weighted object. To simulate the artifacts, it also takes a motion sequence and or eddy-induced gradients. And then we solve Bloch and Maxwell equation, so we can get the time signal. And then we use an inverse Fourier transform to get the image. So the input object is a 4D volume, where the fourth dimension specifies the tissue types with corresponding MR parameters. So here we assume the T2 under different field strengths are the same. So diffusion weighting is simulated by voxel-wise spherical harmonic fitting. So spherical harmonic series is analogous to Fourier series, and here we do it with an order of 8. And we simulated one slice, and with a slack thickness of 2.5 millimeters. And we use spin echo EPI as a pulse sequence with parameters specified here. So with this pulse sequence, we will have zigzag k-space trajectories. And we have several assumptions for the simulation. The first is we assume B0 is homogeneous, and second, we assume the excitation period is significantly smaller than relaxation times T1 and T2, so the effect of the RF pulse can be just modeled as a simple rotation through a flip angle, which is 90 degrees in this case. And we assume body thermal noise is a dominant noise source. And we ignore chemical shift. So the first row is one of my simulation results, and the second row is a series of diffusion images, and the third row is a simulation from the paper, this paper. And from the first column, when B is 0, it is essentially a T2 weighted image, and we can see this method does capture some characteristics of T2 images. For example, white matter is dark, CSF is bright, and with larger B value, which means stronger diffusion gradients, it does capture stronger attenuation in signals. So this method works to some extent. So one may wonder why these images looks different in shapes. So interestingly, even in this paper, when they compare their simulation and the real data, they're using the images obtained from different subjects. And because my simulations may not be using may not be simulating the same slices as their simulation, so it is understandable that they have different shapes. So if we do not consider motion and assume there's no noise, under 3T and 0.5T, the images are essentially the same, or say almost the same, because with EPI pulse sequence, the TR is much larger than T1. So this term here is essentially 1. So the difference between these two images would just depend on T2. And because we assume T2 values are the same under different field strengths, so the image intensities will just be the same under these two cases. However, if we consider noise under lower field strengths, the noise will be much stronger compared to higher strengths. And we can see under 0.5T, the image quality is deteriorated much more seriously compared to the high field. So if we consider motion with a rotation with respect to z-axis, in the image, there would not only be a rotation of the object, but there is also a phase and a blur, which deteriorates the image quality a lot. If there's a translation in x direction, which is the readout direction, there could be aliasing along with blurring. And if with translation in y direction, which is the phase encoding direction, we can say there will be aliasing in the phase encoding direction, and there would also be blurring. So in this project, the main challenges are due to the open sourced code, which is not well organized. And so it takes me quite a while to find the corresponding sections in the paper. And second, because the code I used is dependent on the FSL version, and because of some issue, I can only use my laptop instead of my lab's computer, so the limit and the memory is limited. So I can only simulate one slice in this case. So with more resources, we can simulate the whole brain image, which can help us better understand how motion impacts the image quality. And so from this project, I feel I obtained a better sense of the whole MR imaging process, and it also helped me better understand how motion impacted the image quality with the EPI pulse sequence. And thanks for watching.